Hey everybody, welcome back. Looks like we have pretty close to a finished product here, or at least a finished prototype, I should say. So I've made some final changes, and I think I got a circuit that I like, and I got it to the point where I actually have posted it to my Patreon shared folder, and we're going to listen to this and see how things work out. I'll give you a quick look underneath what the circuit looks like finished. It doesn't look a whole lot different. There's a few changes I made, components I replaced and things, but really not a big bunch of changes. And I think in this video, we'll just listen to it. I'm going to go over the schematics with you, where we are finally. And then the last video, we'll actually get into some extensive testing of the amplifier. You have to remember, this is a prototype, and it is also a vacuum tube amplifier, so it's not going to get the kind of distortion characteristics that you would see on a really high-end solid-state amplifier, just the way these work. But it was quite a journey, and it turned out really good. I'll let you judge for yourself how it sounds, and let's take a look at it. So here's a view of the underneath. It hasn't changed a whole lot since the last video, I don't think, as far as how it looks, but there have been a lot of component changes. We'll get into that when we look at the schematic and why. All I can say is this is pretty much dialed in where I want it. I'm not changing it, and this is what it's going to look like when we put it together. I've flipped the standoffs from the top to the bottom now. So now they act as feet. And then what I can do is I'm going to build a bottom plate that'll screw onto this. So we'll have metal on top and bottom. And then I'll make a nice wooden case to go around it. So let's take a look at the top. Okay, and here's the top of the amp. It's kind of hard to get the whole thing in view because it's so big to get it. Had to back the camera away a little bit. Here are the final lineup of tubes that I have. For the front end, I actually had to change from the 6N1s to a set of 6922s, or 6DJ8s, or 6N23Ps. Any of those will work, or E88CC or ECC88, that family. The reason was I wasn't getting enough loop gain with the 6N2s, or the 6N1s, I'm sorry. And although the amplifier sounded incredible, I couldn't get hardly any feedback. If I applied any kind of global negative feedback, I would run out of gain very quickly, and that would cause stability problems with the amplifier. So as a result, the amp would oscillate. And it wouldn't oscillate if I didn't put hardly any feedback on it, but of course, without having any negative feedback, you couldn't control any kind of things like ringing if we had, but there was very little of that. And the other thing is the input sensitivity was bad. I had to have at least 2 volts RMS, and I really wanted it to be closer to 1 volt RMS. By going to these tubes, I had to make some changes to the circuit, but I got a significantly more loop gain, and that allowed me to get things where I wanted them to be. So we tried it, and it would have worked, but not as well as it works like this. I have a set of Electro-Harmonix 6SN7s and a set of KT88 EHs. And these were all quad matched, so that's good. There's a balance adjustment for the Hedge circuit in the beginning, in the front, which is the long tail pair, cascoded long tail pair. Also have a balance for the bias of the tubes, which is right here. And then we have a bias level adjustment, and we have a test point for each of the tubes, so we can measure both balance and bias. So we'll look at that later. Here's our chokes for the 300 volt supply, which is now a 350 volt supply. I'll get into that when we look at the schematics. Here's our power transformer and 2 outputs. These output transformers turned out to be very good as far as performance goes, but they were a little bit of a challenge because they had a much higher plate impedance than I would have liked when using this transformer for the power. We could get more into that too when we look at the schematics. As I might have said, I have the final schematics are done, and I've compiled them and posted them up on my Patreon shared folder. So my patrons can feel free to download them, and if you have any questions, you guys can email me. You know how to get a hold of me. And yeah, so let's look at the schematic now and see what kind of changes have been made. Okay, let's do the amplifier first, and then we'll do the power supply, because really I made the least amount of changes on the power supply. Now I'll point those out when we look at it. But for right now, so this doesn't bleed through, I'll move the power supply out of the way. So you can see a lot has been removed and simplified and so forth. I tried everything in there, and then I just kind of backed things off as I needed to. And no matter how much you calculate things, there's still going to be some things you're going to have to do by trial and error, because there's just no way that you'll perfectly nail it the first time. I guess if you build these kinds of things a lot, and there are some hobbyists who do a lot of design and experimenting, you probably can get things nailed a lot quicker. But since this is not something I do all the time, it took me a little bit. Let's start here with the hedge circuit, as they call it. I had to remove this capacitor here. And if you remember in the previous version that I showed you, there was this high-pass filter, and the whole idea was to any kind of high HF signal would be shunted to ground. The problem is that caused an imbalance between this side and this side. And therefore, if something happened over here, this wasn't able to follow it. And what would happen was it would actually cause the amp to oscillate. So I had to remove that. The other thing was I could have put a filter on this side to match this side, but then that would have messed around with our feedback circuit a little bit, and I didn't really want to do that either. So by removing this, everything is stable and it works perfectly, so I'm leaving that. I showed you in the previous version where I changed this to cathode bias, and I explained that the fixed bias made it too difficult for things to stay stable, because if things would heat up or change a little bit, it couldn't track, the bias couldn't track with it because it was fixed right here at these grids. So by making it cathode biased, everything kind of tracks and it always falls into equilibrium, which is a good thing on these upper ones here. On the lower ones, the ones that actually handle the signal, I showed you that I removed this, and then I made a couple small changes to the constant current source. I lowered this resistance from 520 ohms to 10 ohms, and I changed this bypass capacitor from 10 microfarads to 1,000. And what that's going to do is that's going to help us with our AC stability and so forth with the constant current source when you start applying an AC signal, not a DC signal to it. So it's just kind of move the low frequency way lower than it was, and it actually worked out perfectly. So that's good. Over here, the feedback circuit, I really had to work with that quite a bit, and the sweet spot turned out to be this combination. Again, I could use a 1K and a 12K, but then you're drawing about 1 milliamp at full power, whereas when I went to 10K and 120K, it still kept the noise to a minimum and gave me the same ratio, the same divider, but yet still low enough values to keep the noise still down. And yes, it is okay for your grid leaks. This is a grid leak when there's nothing connected, and it is part of a divider circuit, divider network, when your feedback is connected. So this is kind of a dual purpose thing. And no, it does not have to match this one. That really, those don't affect one another. I put a tiny little 4.7 picofarad capacitor across this for phase correction. If I get any higher than that, the amp will start to oscillate because it really doesn't like heavy feedback, you know, at high frequencies. So 4.7 was perfect. When you do a square wave now, and I'll show you a square wave on it when we do the testing in the next video, there's just a little pip at the beginning and it's flat, and it doesn't care about what frequency you're at or anything like that, of course, because the square wave is literally a fast rise time no matter what frequency. So that worked out really good. Adding a 1 microfarad capacitor onto the load, again, this handles it very well, and you just get one, maybe 2 little ripples of ringing at the beginning. That's it. So super stable. Most of this is the same. I don't think I've changed hardly anything there. These grid stoppers are 10K each. I think they were originally 1K. I moved them up to 10K. And again, that just gives us a little more stability. And then I added this 22 picofarad capacitor on this side to help with, again, with some phase correction issues that we might have. This is not expressly necessary, but I did notice it did make a little bit of a difference. So I left it in there. It's easy enough to just pop that out of there if, you know, if further testing shows that we need to do that. That's about it. For the bias circuit, we're setting our bias at about 58 millivolts. And that's kind of the sweet spot to get that 70%. These tubes are rated at about 42 watts maximum plate dissipation. And so 70% of that, you have to also subtract because this is an ultralinear circuit, you have to subtract the little bit of screen grid current that you're drawing, because we're making our measurement down here at the cathode. Cathode current is not the same as plate current. Cathode is going to be the plate plus the screen grid, and screen grid is going to be somewhere between 5 and 10% of the current that your plate is drawing. So as a result, you want to add that together and then subtract it, and then measure it that way. You have to kind of remove that. Anyway, it turns out to 58 millivolts, and that's where it's set. Have our balance. So once you do that, you can go across these two resistors from cathode to cathode and use the balance to set it for 0 volts, and that's going to set these identical. That's it. It's a pretty simple circuit now, and it works. Now looking at the power supply, really the only couple changes I made there is C20. It's a 4.7 nanofarad at 2 kV. That is extremely important. The funny thing was, this amp is dead silent. There is almost no sound, no hum or any kind of hiss or anything. It sounds amazing, with no signal. But if you put your ear right against the tweeter, you could hear a 120 hertz clicking sound, just like a, like a click. And whenever you hear that, that's switching noise. Now, normally you won't have that because I use these UF 5408s, and those are kind of a soft recovery, high frequency diode. But it still had ever so tiny of an amount of it. Putting this cap across there just squelched it right out. So that's how I did it. The other way is you can put a capacitor across each diode. But this way, because of the circuit the way this is probably just as effective, if not more. And it works great. It completely killed it. You can put your ear right against the speaker now and you can't hear it. And if there is the tiniest little amount, when I record this and post it, we'll record some silent time. You have to understand the YouTube algorithm, when you record silence on an amplifier, if there is even the tiniest amount of hum, it will massively amplify it when it processes when you go to process the video and the audio, you know, when you upload it to YouTube. It's just one of the things that YouTube does. So if you hear a little bit of buzz or hum in the background when you're listening to this on YouTube, just understand that that's the YouTube algorithm massively amplifying what's there. I can put my ear against the speaker and almost can't hear anything at all. It's that silent, even in a quiet room. But just so you've been warned, that's what YouTube does. And then when you get a regular signal level, it changes the, you know, it lets it open back up again. You know, it adjusts itself. So that compression thing is kind of baked into YouTube's algorithm, and you can't change it. In addition, we have this diode reference network, and I talked about this in the last video for our regulated 300 volt supplies. This went from a 150 volt Zener to a 200 volt Zener. Now I think they do make a 200 volt Zener diode, but I don't have any. So what I did was I put two 100s in series. I made a little note about that right here. So now we have 350 volts coming out of here. And remember, these just make the reference for here, and they're fed directly off the 520 up here. And then this part that's being fed through the pass transistor, that's coming from this source here. So these are coming from the reference comes from a separate source. So no matter what this does here, it's not going to affect the reference here. So that's a really bulletproof, solid way to do it. And then we have this little, I'll call it a helper transistor. It's kind of like, works like a Darlington transistor. And that's where we're feeding in our reference. So it's not going to be current dependent in any way, you know, from all this. Pretty cool. Or at least this isn't. This isn't going to draw any appreciable current because it's going to use the gain of this transistor to drive the base of this transistor. And again, we're at 350 volts. Now, I had to raise these voltages to 350 because these 6922s need a little more headroom. They need a higher voltage to be able to get their full amount of swing. At 300 volts, the amp worked, but I couldn't get full power. It started to like round over the waveform as you started driving it harder. By going up from 300 to 350 volts, that eliminated that, and it's perfect. So we're at 350 volts for the preamp section, and then we still have our 530 here. Other than that, this power supply hasn't really changed at all. It's exactly the way it was in the last video. Okay, let's turn the amplifier on. And the first thing I want to do while after this thing warms up here for a few seconds, is I'm going to take my microphone off right here. And I'm going to turn you around here. Hold on. And I'm going to put you right up against the speaker here, and you can tell me if you can hear anything or not. Do you hear anything? I didn't. The amp's on. So now let's connect up some music, and let's play a silly song. I put this at the end of one of my other videos, and it's one of those, I'll say it's AI generated. It is. I used that Sumo thing, but I wrote the words, the lyrics, and I suggested the key signature and all of that. You can actually kind of guide it how to work, you know, how to write a song. It's still kind of stupid compared to what, you know, a real musician can do. But when you're doing it for fun, it's not a problem, you know. My daughter's a music major, and I can tell you they can do things that the computer can't. Just, they have the personality. Anyway, let's put some music on.
The wheel is turning, but the hamster's dead. Poor old critter ain't moving in my head. I can't remember 'cause the wheel is turning, but that hamster's dead. Well, I burned my fingers soldering up the Placider today. It don't matter 'cause I soldered it in backwards anyway. I plugged it in and turned it on, and the sparks began to fly. That capacitor's insides blew out and hit me in the eye. The wheel is turning, but the hamster's dead. Poor old critter ain't moving in my head. I can't remember what I just said, 'cause the wheel is turning, but that hamster's dead. When I was young, my grandpa said, let me tell you now, measure twice and cut it once, and he showed me how. I can still hear my grandpa giving that advice just after I done measured once and had to cut it twice. The wheel is turning, but the hamster's dead. Poor old critter ain't moving in my head. I can't remember what I just said, 'cause the wheel is turning, but that hamster's dead. Yeah, that wheel is turning, but that hamster's gone to bed.
All right, quite a bit of silliness there in that song. But anyway, you get the point. It works really well. I was actually shocked at how good this thing sounds. And I'm not just saying that. I really didn't, being a prototype, I didn't really take a whole lot of time with the wiring, layout and so forth, with lead dressing and all that. And kind of did a few little things that I knew would control it a little bit, but I kind of expected to have a little bit of hum in the background, but I just can't believe how quiet this thing is. And as far as sound, it's good. Now, the one thing I will say is this amplifier is, I'm going to call it a 40 watt to 42 watt amplifier. And the reason I say that is my original target was to get this thing to be a 50 watt amp. And I was not able to reach that, and the main reason for that is my choice in transformers. I really thought that the B plus of this transformer would be sufficient to drive the amp to 50 or even 60 watts. The issue is the output transformers have a really high plate impedance, which you don't really see that much with big power tubes, especially like with KT88, 6550s, or if you're using a quad of 6L6s or something. You normally see a lower plate impedance, like down in the 1.5, 2K, something like that, 2.5K. This thing's like 4 point something K, 40 some hundred ohm, plate load. And what that's going to do is that's going to make you need to have a much higher B plus. You just have to have a different power supply and a different topology to get that full power out of it. Now, the reason that they did that is these transformers were designed for absolute, lowest distortion and cleanest delivery of signal and so forth. And it, in fact, works for that. The trade-off is by having that higher impedance, you're never going to get a real high power output without exceeding the limits of the tubes and so forth. So it's a trade-off. If you're looking for just raw high power, this is not the setup you want. But the difference between 42 watts and 50 watts, from a dB standpoint, is really minimal, especially to your ears, sound pressure wise. So I don't think it really matters at the end of the day. But I know some people just get their needle stuck on watts, watts and THD, and that's all they think about. That's all they care about. And I think you just need to learn a little more about how this stuff works to appreciate why that's not as big of an issue as many people make it out to be. So anyhow, I hope the amp spoke for itself, and the next video I'm going to set this up, and we're going to do obviously a frequency analysis and phase shift analysis. We're going to check the THD, which I'm going to tell you is not that low. This is not going to be like a solid state amp. It's going to have 1% THD, even 2%, at full power, at clipping. You're just going to see that because this is a tube amp, and unless you're talking about a unity gain or a unity coupled amplifier like what Macintosh does, you're just not going to see that kind of distortion figures. Maybe some of these really boutique 3-watt, inefficient Class A, with great big transmitting tubes to put out a couple of watts, 1500 volt supply. Maybe those can get some pretty low distortion figures, but anything like this, especially Class AB, you stay in, under 1% at full power, and you stay, this is at 1 watt, this is going to do about 0.1 to 0.2% THD, but it's where the THD comes from that makes the big difference. So we'll talk more about that as we start characterizing the amp and testing it. But that's it for right now. I'm on the other side of all the hard work and all of the training classes and things I was in, so life is getting a little bit back to normal. It's the day after Thanksgiving right now, so I have a long weekend. I do have some things I have to do for my daughter and son-in-law because they're moving into a new house. But other than that, I should have some more time to play at the bench this weekend and get you another video a little bit sooner than the last one. So until then, I wish you all peace, joy, happiness, and good health in your lives, and hope to see you again real soon. Take care, everybody. Bye-bye.